Welcome to the Walton Pi. Today we're going to be going through a test review for the first part of Calculus 1. So let's start off with some potential problems that we might come across on a test. For example, we might be given some sort of table that then has both position and time. So we have some position function and some time function, and we might be given some information like we know some information at time 0, time 5, time 10, time 15, and time 20, and maybe this is in seconds, for example. And then our position might be different values here, so maybe it's 3, 12, 13, 21, and 23, for example. And this might be position 0, and this might be like position 25. And then we could be breaking this up into some different sections. So this is 5 meters down the hallway, this is 10 meters down the hallway, 15 meters, 20 meters, 25 meters, and we have all of these different positions. We could think of this as saying, at time t equals 0, we are right here at 3 meters. So this is t equals 0. And then we are walking this direction at some different speeds. So after, for example, 10 seconds, we are at 13. So we would be right about here at t equals 10. So this is the sort of thing that it's representing. It's maybe mapping the position of where we are in the hallway, things like that. What we could do, though, is once we have this, we can try and figure out what interval do we, or like what's our average velocity? So we might be asked, what is the average velocity? So what is the average velocity over this time interval? Go ahead and pause the video and then try it on your own, and then we'll be able to talk about this in a sec. So the way we could do this is we can recognize that velocity is equal to some distance divided by time. So our average velocity over this entire interval is the total distance we traveled divided by the total time it took. So our average velocity is going to be 23 meters minus, because that's how far we traveled, over the 20 seconds. So 20 minus 0, so this is 20 over 20, so this is equal to 1 meter per second. That would be our average velocity. But then other things we might be asked is, what interval has the biggest average velocity? Go ahead and try and figure out if the interval from 0 to 5, 5 to 10, 10 to 15, or 15 to 20 would have the biggest average velocity, and what that would be. So for these different intervals, let's say we have 0 to 5, 5 to 10, 10 to 15, and 15 to 20, we're trying to figure out which of these has the largest average velocity over that specific time interval. What we could do is we could go and figure out what's the velocity over each of these different intervals. So we might have, we might make a table to figure out the velocity. So the velocity from 0 to 5 seconds, our change in position would be 12 minus 3 divided by our time, which is 5 minus 0. So this is going to be 9 over 5. Okay, so we're going 9/5 per second. From 5 to 10, that's pretty slow. It's just 13 minus 12 over 10 minus 5. So this is going to be a 1/5. So the time interval from 5 to 10 is definitely not the fastest time interval. But then maybe from 10 to 15 we might get something else. So that would be a 21 minus 13 divided by 5. So this is going to be 8 over 5. And then 15 to 20, that's going to be 23 minus 21 divided by 5, or 2/5. So from here we'd be able to figure out what's the fastest, what interval has the fastest average velocity, and that would be the interval from 0 to 5. So this is the sort of thing that we talked about near the beginning of class or the beginning of these videos when we're going through different things of velocity and trying to figure out how can that help us with these sorts of things, and this is where calculus will be helping us be able to do more along these lines. So the next thing that we have is to try and figure out which of the following are functions. So I'll write these down and then give you a moment to pause the video to try and figure out which ones are going to be functions, and then we will talk about them as a group. So which of the following are functions? We have y squared equals 5x plus 2. We have y equals the square root of x plus 4. We have x squared plus y squared equals 4. Y equals sine of x over x. We have y equals 1 over x squared plus 1. And we have y squared minus x squared equals 13x. Go ahead, pause the video, and try and figure out which of these are functions and why. We might recall what does it mean for something to be a function. For something to be a function, it means that we have one input, one output. So that's what it means for something to be a function, and in this case we're going to be assuming that our outputs are our y values and our inputs are our x values. So let's go through each of these and try and figure out how many for 5x plus 2. If I x value, is it possible for there to be more than one y value that works? Well, for example, if we were to plug in x equals, let's say we put in x equals 0, for example, then we have y squared equals 2, and there's two different y values that work. We could have y be positive or negative square root of 2. So because there are two different y values, this is not a valid function. So that is not a valid function. How about y equals the square root of x plus 4? If I put in an x value, is there only one y value that works? Yeah, there's only one y value that comes out from putting in a single x value. Now we can't put all x values in, because not every x value is in the domain. But on the how about x squared plus y squared equals 4? That's not a function, again because we could get more than one y value for a given x value. Like if we put in x equals 0, then y could be either positive 2 or negative 2. But we can also see that by looking at the graph and looking to see does it pass the vertical line test. This one, there's two different places where that vertical line, so this is not going to be a vertical line test, so it's not going to be a function. How about y equals sine x over x? If we put in a given x value, is that always going to give us out a y value? Well, if we put in any x except 0, we're going to get something out, but that's totally fine. That's just something involving the domain. But if we put in an x value, we can't have more than one y value that works. So this one is also going to be a function. Same thing for y equals 1 over x squared plus 1. That's also always a function. We don't get more than one y value out from a given x value. However, the last one, y squared minus x squared equals 13x, is not going to be a function, because we can get more than one y value coming out from a single x value. So out of all of these, hopefully you were able to figure out which ones were functions. Okay, let's now talk about even and odd functions. So let's go, which of the following are even? Let's first figure out which functions are even functions. We got 3 cubed plus x. We got sine of x cubed plus 5x squared. We got cosine of x plus x squared. We have 1 over x squared plus 1. And let's also have 3x plus 5. Let's go and try and figure out which of these are going to be even. So go ahead and pause the video, try and figure out which ones are even, and then we'll go through them all together. So remember, a function is even if f of negative x is the same thing as f of positive x. So it's even if putting in either positive x or negative x doesn't change the function. So let's go through and try it with each of these to see how many of these are going to be even. So for 3x over x cubed plus x, we are going to replace every x with a negative x. So that gives us 3 times negative x over plus negative. Go through and simplify that. Here, let's make a little bit more space. So if we were to simplify that, the top becomes negative 3x, and then the bottom, negative x cubed, and then we have a minus x. Well, we have a whole bunch of negatives, so we could multiply the top and bottom by a negative 1, and that's going to give us 3x on the top and x cubed plus x on the bottom. Well, that's the same thing that we started with, so this one is going to be even. Okay, how about sine x? Well, let's check sine. What is sine of negative x? Well, this is one of those properties that sine has, and it's one of the ones that's useful to remember. Sine of negative x is equal to negative sine of x. So this one is not going to be even. However, we might recognize that this is the definition of something as being odd. So we could go and figure out, or remember, that f of x is odd if f of negative x is equal to negative f of x. So sine of x is going to be odd. How about x cubed plus 5x squared? What happens if we plug in negative x to that? Well, we get, oops, there we go, that we get negative x cubed plus 5 times negative x squared, which is negative x cubed plus 5x squared. Okay, so that's not even because it's not exactly the same because we have this negative sign out front, but it's also not odd because this plus is also not a negative. So this one's not even and it's not odd, so this one is neither. It's neither even nor odd. Let's go and look at some of these other ones that we have. So let's look at cosine of x plus x squared. If we replace all of the x's with negative x, we get cosine of negative x plus, whoops, negative x squared, which is one of the properties of cosine is that cosine of negative x is equal to cosine of x, so that we get cosine of x plus x squared. So that means that this one is even. It's the same whether we put in a positive or a negative x. How about 1 over x squared plus 1? Well, replace all the x's with negative x, and this is 1 over x squared plus 1. So this one is also even. Now, this curve has a funny name. This is what's often referred to as the witch of Agnesi. No idea why it's called that, apart from like maybe the graph of it kind of looks like a witch hat, because it looks, I don't think that particularly looks like a witch hat, but regardless, it has that like fun little name, but this is an even function. Let's finish off with 3x plus 5. If we plug in negative x everywhere, we get 3 times negative x plus 5, so that's a negative 3x plus 5. And this is not going to be even because it's not the same, and it's not odd because we don't have a negative sign right there. So this is neither even nor odd. So if you were able to figure those out, great. If not, maybe something that you should study a little bit more. Let's now talk about some domains. Okay, for the next one, let's find what is the domain of f of x equals sine of 7x divided by 5x plus 2, and then g of x equals log base 3 of 5x plus 4 times minus. Try and figure this out. You need, and try and figure out what the domain of these functions are. Okay, so to get started, let's remember the 3 things that we can't do. So we cannot divide by 0, take the logarithm of any base of 0 or a negative number, and we also can't take the square root, of a negative. So those are the things we cannot do, and technically the square root could be any even root, but in general that's the one that we see the most often. So those are the 3 things that we cannot do. So for f of x, do we have any division? Yeah, we're dividing by 5x plus 2. That means we need what's on the bottom to never be 0. That means we need 5x plus 2. That cannot be 0. Not be, whoa, go back to normal. So that means that x cannot be negative 2/5. So that took care of we can't be divided by 0. Are there any logarithms? No. Any square roots? No. So that means that all 3 of these are taken care of. So the domain of sine of 7x over plus 2 is x cannot be negative 2/5. So this would be one way we could write the domain. Also write the domain in interval notation, which would be from negative infinity to negative 2/5, unioned negative 2/5 to positive infinity. That would be how we would write the domain. One of those 2 ways is a valid way of writing it. Let's now figure out what the domain of our second function is. So let's clear out the things that we use to keep track. Are we dividing at all in this problem? No, there's no division, so that means that we aren't dividing by 0, so great. That's one of the 3 things checked off. Next one, logarithms. Okay, we can't be taking a logarithm of 0 or a negative number, so that means we need 5x plus 4. It needs to be strictly bigger than 0. So let's go through and solve what that's going to be. So then we get 5x has to be bigger than negative 4, so x is bigger than negative 4/5. So there is one piece of our domain. However, we are also multiplying by this square root thing, which means that we also have to deal with that one. So this is going to tell us that x squared minus 1, we can't be taking the square root of a negative, so that means that has to be positive or 0. So that's greater than or equal to 0. So x squared is greater than or equal to 1. And at this point we might want to say, well, let's take the square sides, So then x is going to be greater than or equal to 1. But that's not quite true. The square root of x squared is the absolute value of x. If you're trying to figure out why that is, what's the square root of negative 3 squared? Well, that's the square root of 9, which is 3, which isn't negative 3. So what we have here is this is going to split up into two different things. Either x is strictly bigger than or equal to 1, or x is less than or equal to negative 1. So these are the three things that we are going to have to look at. Now, trying to combine all of these together into interval notation might be a bit hard to do, but what we can do is we can go through and figure this out, sometimes using a number line, or if you're familiar with sets, you can look at intersections of those. But let's look at these as a number line. So on a number line, we have three different points that we care about. We have -1 and something that happens at -4/5. What we can do is we can draw on this number line all three of these things to figure out what is the interval going to be. So the first one is x has to be bigger than -4/5 in order for log base 3 of 5x plus 4 to make sense. So that means we would start here at -4/5, and then we would continue along in this direction. And we would continue forever, but we don't include -4/5. The next one is we would want, well, or, so that means we are either going to start here, include it, and then go that way. Come on, draw. And then go that way. What we have to do now is we now have to combine all of these so that both of these conditions are true, that we have both this and this true at the same time. And what's the interval where that's the case? Well, that's going to be this interval here. It starts at 1 and we include it that way. So that means our interval is just x is greater than or equal to 1, or in interval notation, it would be starting at 1 and going to infinity. That's how we would write the domain of this function. Let's now talk about how we would graph functions and how we would be able to use some of those like vertical shifts, horizontal shifts, and translation. Alright, so the first one we're going to do is we're f of x equals 17 minus 3 times x minus 4 squared. Go ahead, give that a shot, pause the video if you need, and then we will continue on and figure this out. Okay, so let's go through and figure out how would we graph this. Well, the first thing that we would do is we want to figure out what's our very basic, most underlying function. And that's going to be x squared. We have just a simple x squared showing up. So the first thing we would do is probably graph that. So here is a graph of x squared. So this is our first function that we started with. What's the next thing that we would do? Remember, if we're trying to figure out the order of operations, we can often do that by remembering PEMDAS. So PEMDAS, where P stands for parentheses, E is exponents, MD is multiplication or division, and then AS is add subtract. Because we have these parentheses here, under the x minus 4 all squared, that's going to be the next thing we want to do. So we are going to then want to figure out what's the next function we're going to do. That is going to be, let's do this one in blue, x minus 4 squared. So think about this for a moment. What is that doing? Well, x minus 4 squared, if we're trying to remember, okay, that's a horizontal shift of some sort, but is it shifting it 4 blocks to the right or 4 blocks to the left? Well, if we are subtracting 4, that means that this is behaving like 0 in x squared when x is equal to 4 in the x minus 4 squared. So we knew that it was 0 so it was equal to 0 when we put in 0 for x squared. Now if we put in 4 into x minus 4 squared, that's also going to be 0. So we need to go over 4 blocks, 2, 3, 4, and now it's going to pass through this point. So that graph is something like that. It's kind of hard to sketch, but that one is our x minus 4 squared. What's the next thing that we would do to this? Well, the next thing that we do is we're multiplying the x minus 4 squared by a negative 3. So the next thing we would graph is negative minus 4 squared. So 3 would stretch it by 3, but then the negative is also flipping it. So we are going to end up with something that's like that. So this is our negative 3 x minus 4 squared. And then the last thing that we're doing is we have a 17 added to it. So we have negative 3 times x minus 4 squared plus 17, which is the same thing as our f of x. So now we are shifting up our gold graph up 17 blocks. So it's going to be something like this. So this is our function f of x. Now, to make sure that they know exactly what you're doing, I would probably label the vertex, because we know exactly what it is. We shifted it over 4, and then it went up 17. So this point up there is 4, 17. And so that's how we would go about graphing 17 minus 3 times x minus 4 squared. You could plot a couple other points if you wanted to, but that would be the process that we would be going through to do. Let's do another one. So graph g of x is equal to 5 times sine of 2x minus 3 pi. So go ahead, pause the video for a second, and figure out how could we graph that on this chart. Okay, so while I'm finishing up putting the touches of our scale on this graph, let's start by figuring out what's our baseline function. Well, our baseline function is just sine of x. That's just where we're starting. So let's start by figuring out what's the graph of sine of x. Well, let's see. What are some of those points that we know? So we know that sine of 0 is 0, so it's going to pass through 0, 0. Let's see, sine of 2 pi is also 0, so it's going to pass through there. It'll pass through 0 at 4 pi, negative 2 pi, negative 4 pi. But then it's also going to be 0 on each of these other multiples of pi. So here at 2 pi, it's also 0. So we know it's 0 all of those spots. Let's see, where is sine equal to 1? Let's see, that's going to be at pi halves. So if that's 2 pi, pi halves is here. So it's going to be going like this. So we can start to figure out what's the graph of this look like. Well, the graph of sine of x is going to be about this. We were able to figure this out using a few points that we knew and go through and figure that out. So there is sine of x. Now, what's the next thing that we would need to do? Remember, we have to follow the order of operations. So the next thing is anything that's inside parentheses. So it's sine of 2x minus 3 pi. So we're going to have to first figure out, do we subtract the 3 pi or do we multiply the inside by 2 first? Well, multiplication comes before addition and subtraction. So we're going to look at what's the graph of 2x. Now, the graph of 2x, so sine of 2x, that's our next thing. If we are doubling our x values, think of it a little bit. That's going to be doing something to our horizontal thing. Now, is that going to compress it by 2, or is that going to stretch it by 2? Think about that for a second. It turns out this one's going to be compressing it by 2. So that means everything's going to happen in half the time, because we are basically getting everywhere twice as fast. So that function is going to be doing something like this. Okay, so there's the graph of sine of 2x. And then the next thing is we're going to do a sine of 2x minus 3 pi. So minus 3 pi, well, that's shifting it to the right 3 pi. So that means that everything is going to be moved over 3 pi. So if we were to look at where does this one curve go, that is being moved over 3 pi spots. So instead of starting at 0, it starts at 3 pi. That's moving to be right there. Oh, wait a second. That's matching up perfectly. So it turns out that this blue curve is both sine of 2x and sine of 2x minus 3 pi. That's weird. But we could figure that out, that's not changing anything, by using some of those sine addition formulas. So go ahead and look back to see what those are, so that you can be able to see and justify the reasoning for why is sine of 2x minus 3 pi not actually changing anything. Because that's a really cool thing. So the blue one is also our gold graph. So these two are the same. But then if we're trying to figure out the last bit, we have a 5 times sine of 2x minus 3 pi. What's that one doing? Well, the 5 is on the outside, so it's stretching everything by 5. So instead of having a peak here at 1, we'd have a peak 2, 3, 4, 5. So it's this really steep curve that goes up and then down and then up and then down and then up. And it's just this really steep, really frequent curve that we'd be able to go through. And so that is going to be our 5 sine of 2x minus 3 pi. And then, of course, it would go backwards on the other direction as well. But that's how we would be able to go about graphing this sort of thing. Alright, let's do something new now. So let's start practicing how we would be able to solve for x given different equations. So suppose that we are asked to solve for x from the following two equations. So the first one is e to the 5x minus 2 is equal to 3. And the other one is sine of 2x plus pi thirds is equal to 1/2 on the interval 0 to 2 pi. So go ahead, try both of these, try and solve for what x would be in each of these cases, and then we will go through it together in a bit, so feel free to pause the video if you need more time. Let's start with the first one. We need to somehow get this x all by itself. Now the challenge with that is it's inside the exponential of something. So we're going to need to use the inverse of an exponential. So the inverse of e to something is the natural log. So we're going to look at the natural log of e to the 5x minus 2. That is equal to the natural log of 3. Great, so the natural log of e to that stuff is just going to be that stuff. So we got 5x minus 2 is equal to the natural log of 3. Now to solve for x, let's add 2 to both sides. So we get 5x equals the natural log of 3 plus 2. And then we can divide everything by 5 to get x equals natural log of 3 plus 2 all over 5. And that's what x is. That's not a nice number to write out as a decimal, but it is a valid answer, and it is in fact the solution for that problem. let's try and do something similar for the second one. If you didn't get it, try one more time to try and figure out if you can figure out the answer to this one. Okay. So to solve this one, we might want to say, well, we're going to just do the inverse sine function. So we might say it's going to be inverse sine of 2x plus pi thirds is equal to inverse sine of 1/2, which is a perfectly valid thing to do, except this is only going to give us one of the solutions. So if we go through and do this, the inverse sine and the sine would cancel, and we'd get 2x plus pi over 3 is equal to inverse sine of 1/2. What's that going to be? Well, inverse sine is, at least on the unit circle, if we're looking to see where is that going to give us valid answers, sine is our x value, so that's giving us, or no, sine is our y value, so that's giving us an angle in this region here. And sine of those angles, well, sine is the y value, so that's a height, so that's going to be right here at pi 6. So this is telling us that this is equal to pi over 6. Now, that's only one of the solutions. What we could do is, there's also a different angle out here that would also have gotten us that same y value. However, inverse sine only gives us the one from negative pi halves to positive pi halves. We have to then use that to work with to figure out the rest of the angles. So we could get 2x plus pi thirds is pi over 6, but we could have also gotten 5 pi over 6. Or we could have gone around the circle once and then stopped there, so we could have also had 13 pi 6. And then there's nothing stopping us from going around the circle and then stopping here at 17 pi over 6. And we could keep going around and around and around to get a whole bunch of these different things. Now the question is, how many of those do we actually have to care about to try and figure out the answer? Well, let's just try a few and see when they start being inside our interval and when they stop being inside our interval. So by doing that, we could then subtract pi thirds from everything. So we'd get a 2x is equal to, let's see, pi 6 minus pi thirds. Pi thirds is 2 pi over 6. So that's another way we could write it. So subtracting 2 pi over 6, that would give us a negative pi over 6, 3 pi over 6, 11 pi over 6, let's see, 15 pi over 6 would be the next one. Let's see, we could then get all the way up to another 2 pi after 11 pi over 6, so that'd be another 12 pi over 6, so we could also get 23 pi over 6 and 25 pi over 6. So these are just a whole bunch of them that are all solutions, and we could then divide everything by x, or not by x, by 2, and we would get x is equal to, let's see, a negative pi over 12, 3 pi over 12, 11 pi over 12, 15 pi over 12, 23 pi over 12, 25 pi over 12. And now we need to figure out how many of these are inside our interval 0 to 2 pi. Well, 0 is 0 pi over 12. So that means one spot we would have to stop would be here at 0 pi over 12. So that means this one's not included, but we would be starting right here. And then 2 pi is 24 pi over 12. So we would be stopping right between here. So that means that these are the 4 solutions to sine of 2x plus 3 pi equals 1/2. Those are the 4 different solutions that all work. Now, just because the inverse is canceled does not mean that that's the only solution. This is similar to those situations where we have something like x squared equals 5. We don't say that, oh, then x must be the square root of 5. It could be either the positive or negative. It's just when we're dealing with sines, there's the possibility of a lot more than just the positive or negative version. We have a whole bunch of different ones that we would all have to check and include all of them. Let's now go through and do some inverses. Since we've been using them, let's now practice finding the inverses. So, find the inverses of y equals 7x plus 3, y equals 5e to the 4x plus 3, and y equals 5 tangent of 3x minus 2 minus 4 on the interval, open interval, 2/3 minus pi over 6 to 2/3 plus pi over 6. Go ahead, give these a shot. I arranged them in order of difficulty. So go ahead, give them a shot, pause the video if you need, and we will go through them all together. Okay, so for the first one, so there's a couple ways that we could do this. A common one is to switch the variables x and y and then solve for y again. So if we were to do that, we would get x equals 7y plus 3, and now we're trying to solve for y. So we'd get x minus 3 equals 7y, so then y is equal to x minus 3 over 7. That's one way we could do it. The other way is you could solve for x at the start and then switch the variables. It doesn't particularly matter which one you do, but that is what we're going to be trying to do. So this is our inverse of our first function. Let's now do that for our second function. So switching our variables, we get 5e to the 4y plus 3 equals, and now we want to solve for y. So because we have the e, we might want to just take the natural log of both sides, but the problem with that is by taking the natural log before we've gotten rid of this 5 in front, we can't cancel the natural log and the e. The natural log and the e have to be right next to each other. So before we take the natural log, we would need to divide both sides by 5 to get e to the 4y plus 3 equals x over 5, and then we're able to stick a natural log on this and have things cancel. So to get a 4y plus 3 equals the natural log of x over 5. Well, to solve for y, we need to subtract the 3, so 4y equals natural log of x over 5 minus 3. So y is equal to the natural log of x over 5 minus 3 all over 4. And that is going to be our inverse function for this particular function. Now, this last one is probably the most tricky to figure out. So let's start by switching our variables. So 5 tangent of 3y minus 2 minus 4 is equal to x. Well, let's start by adding 4 to both sides and then dividing by 5. So we'd get tangent of 3y minus 2 is equal to x plus 4 divided by 5. So I did two steps together. First added 4, then divided by 5. And now we need to get rid of our tangent sort of thing. So, well, let's just use the inverse tangent. And now we just have to take care that this is going to be using the correct interval. And in this case, it turns out that it is. If we were to go through and check, like, okay, is this on the correct interval? Like, I plug those values in for x. So you plug these in for x in this top one, and is that then making it so we have tangent of things that go from negative pi halves to pi halves? And in this case, it turns out that it is. So we are in the correct interval for inverse tangent to actually cancel everything out. If we weren't, we'd have to shift things by some units of pi to get them to be the correct inverse. But what we can do is we can now take the inverse tangent of both sides, and we would get 3y minus 2 is equal to the inverse tangent of x plus 4 over 5. Well, add 2 to both sides, so we get 3y equals inverse tangent of x plus 4 over 5 plus 2. And then divide by 3, we get y equals inverse tangent of x plus 4 over 5 plus 2 all over 3. And that would be our inverse function for this particular case. These can be a bit tricky, but try and just follow your process and go through each of those things, and you should be able to get to the right answer. Now that we're on the topic of inverses, let's do some simplifications with inverse trig functions. So let's say, for example, that we are asked to find what is tangent of inverse sine of 2x. Let's say that we're just asked to do this. Maybe this is a free response, it's like find this. Or maybe it's a multiple choice and they're asked like, which of the following is this equal to? And you have to go through and figure that out. I would always recommend going and drawing a picture for this. So let's look at what does this represent? Inverse sine of 2x. Well, inverse sine of 2x, this is going to give us out some angle. So sine, or the trig functions, they take an angle and give you a ratio. Inverse sine, or inverse trig functions, take in a ratio and give you out an angle. So this is interchangeable with saying that 2x is equal to sine of theta. Okay, so sine of theta, I can visualize that. I can visualize what that's doing on a triangle. So if I draw a triangle, let's say this is theta, this is a right angle. Okay, sine, let's see, if I remember correct, it's going to be SOHCAHTOA. So we can figure out what all of these different things are. So sine is the SO part, so that's going to be opposite over hypotenuse. Okay, so this over this is equal to 2x. Let's see, I can pick anything that works for that. So let's say that I have my opposite side just be 2x, and my hypotenuse be 1. That's an easy choice to make the ratio be 2x, because I can make that 2x over 1. Now, what is this last side going to be? How can I figure that out? Well, the Pythagorean theorem. So we have that side could be a, so we know that a squared plus b squared, so 2x squared, is equal to our hypotenuse squared. So we get a squared plus 4x squared equals 1. A squared equals 1 minus 4x squared. So that means that a is going to be the square root of 1 minus 4x squared. So we now have that side. We figured out what it is. So that's the square root of 1 minus 4x squared. And now we're asked what's tangent of that angle, theta. So this is just tangent of theta. Okay, tangent, that's opposite over hypotenuse, or no, opposite over adjacent. Oh, we already have all of those. This is just going to be our opposite side, 2x, divided by our adjacent side, the square root of 1 minus 4x squared. There we go. This is what we can do no matter what trig functions they stick together and what they put inside. What you can always do is take whatever this is and rewrite it as some angle theta, so that we can then construct this triangle to solve for the missing sides. And once we have the sides, then it's just a matter of figuring out, okay, what's the ratio of what I'm asked to do? This is how we can be able to approach any of these sorts of problems. Okay, we're about the halfway point, so go ahead, pause, take a break, stretch, maybe like practice juggling for a bit, like get some blood moving. Same thing if you're like taking a test and it's not timed. Once you're at about a halfway point, or you're just starting to get a little bit overwhelmed, take a little shake break. Like just like put down the test, like close your eyes, shake a little bit, just get some blood moving a little bit if you can. Try and take a little break. So now that we've gotten there, let's start talking about some limits and stuff. So I'm going to draw a graph, and then we are going to try and figure out what's the limit as we approach different values. So here's our graph. It's doing something like this. Like, this is what the graph is, and let's say that this is a. If we're asked to figure out what's the limit as x approaches a of f of x, well, that's saying as our x values are getting closer and closer to a from both sides, is this approaching some value? Well, as we approach there, our y values are following along this curve up until they get to about here from one side, but they're doing that on both sides. So this is equal to whatever this value is. So maybe if this is equal to L, we would say the limit would be whatever that value is. However, if we are approaching some other value b, for example, the limit as x gets close to b of f of x, this does not exist. Why? Well, if we approach from the left-hand side, we're getting closer and closer to this value up here, but if we approach from the right-hand side, we're getting closer and closer to this value down here, and those are different. So because those are different, the limit does not exist. However, we could specify, that's going to this value at the bottom, because we are approaching from the positive direction. Or if we had instead approaching b from the left, that would be this value up here, because that's the value from the negative direction. However, leaving it as is, where we're just saying the limit as x goes to b, that limit does not exist because it's going to different values. So let's now do a couple examples of this. Let's figure out what is the limit as x approaches 3 of x minus 3 squared minus x squared over x minus 3. And as another one that is similar, let's do the limit as h goes to 0 of the square root of 4 plus 2h minus 2 all over h. Go ahead and tackle both of these to try and figure out what these limits would be. Remember, you can use some of the limit laws, but sometimes we might have to do some stuff before we're able to use those. Go ahead, give these a try, pause the video if you need time, and then we will go through them together. So the first thing I would do is I would try and plug in a number, or plug in the value we're trying to have it go to and see if it works. If it works, great. Like that's absolutely perfect. We're able to get there. However, if we try and plug in 3 into this first one, we're going to get we get a 0 squared minus 9 all over 0. So that's a negative 9 over 0. Negative 9 over 0. That sounds like it shouldn't exist. And it turns out this one does not exist. This is not of the form 0 over 0. So this is not going to give us something that we're able to go through and evaluate. This is a limit that does not exist. However, the other one is a limit that does exist. Because if we were to plug in 0, we'd get the square root of 4 plus 0, so that's the square root of 4, which is 2. So 2 minus 2 is 0 divided by 0. Oh, this one's 0 over 0. Great, we can't plug in. So what are we supposed to do from there? Okay, what are some things we could try? So if we look at this, so we have square root 4 plus 2h minus 2 over h. Well, we have this square root, and ideally we want to find something so we can just cancel that h, but we don't have that yet. So what we have to do is we have to figure out how can we get rid of that square root on the top. That's just a problem. I don't care if the square root ends up on the bottom, I just need it gone from the top. So what we might try and do is say, well, what if I just take everything and multiply by the top again. Like multiplying by the top, that's basically squaring it, so that should get rid of the square root, right? So if we do that, what we would end up with is on the top, we'd get the limit as h goes to 0 of 4 plus 2h minus 4 times the square root of 4 plus 2h plus 4. It's not exactly what we were hoping for. We'd hope we'd have gotten rid of the square roots. So, is this wrong? So this isn't wrong. We did multiply by 1, so this is still true. It's just not helping us get to a point that we would like to be at. It didn't help us get rid of the square roots. So this is what a lot of mathematics is. It's not necessarily, oh, I didn't simplify, so I did something wrong. This is more like, oh, I did something that's correct, it's just not helping me get to a closer solution. It's the same thing as multiplying by like 3 over 3. In this case, it just didn't help us. But squaring it by multiplying by just whatever the top was is really close to something that is really, really helpful. Instead of multiplying by the same thing, let's change the sign of the addition to actually be addition instead of subtraction. If we were to do that, the bottom limit will actually turn into something that's really, really helpful. This is going to turn into the square root of 4 plus 2h squared minus 2 squared. Wow, like that's a lot simpler than the last one. But it turns out that this is a common process. This is what's called the conjugate. And so multiplying by the conjugate is something that's very helpful very frequently, especially when we have the square roots somewhere. If you have a square root with some sort of addition, whether that be this subtraction or this addition in either your numerator or your denominator, multiplying the top and bottom by the conjugate is often something that would be helpful. Now, it's not super helpful when there's not square roots, but sometimes it is. But that's just something that'll take practice and recognition to be able to get to the point of being able to do. So we get this, and then the bottom is this. So if we expand the top, well, square root squared, that's the same thing as just canceling out the square roots. So this top just becomes a 4 plus 2h minus 4. Well, 4 minus 4, those go to 0, those will cancel. So we then have the limit as h goes to 0 of 2h divided by h times the square root of 4 plus 2h plus 2. Well, we have 2 times h divided by h. Those h's will now cancel. And now we canceled out the thing that was making us divide by 0. So before we're trying to simplify anymore, I would try and see if I plug in 0 now, is that still going to cause a problem? Well, if we plug in 0, it turns out we don't get a problem. It's going to just be 2 over square root of 4 plus 0 plus 2. So that's a 2 over the square root of 4 plus 2. 2 over 4 is a 1/2. So that means that this limit that we started with up here at the top, that is just equal to 1/2. And that's how we'd be able to go about doing it. That is how we can solve this problem. Let's do another one. And this one we're going to want to be doing with limit laws. So let's say we are asked to find the limit as x goes to 2 of the square root of x cubed minus 2x squared plus x minus 2 all over x squared plus 3x minus 10. And there is also a plus 3 inside the square root. Let's go through and figure out how to do this. So first, try this on your own. Try and figure out which limit laws am I using, and then we will go through it together. So pause the video and go ahead and try this on your own. Okay, so the first thing we would want to do is, if I just plug in 2, what happens? So plugging in 2, that means we'd have the square root of 8 minus 8 plus 2 minus 2 all over 4 plus 6 minus 10 plus 3. So this is the square root of a 0 over 0 plus 3. Great. I can't do this. I can't plug it in and it works, which is a bummer, because otherwise we'd have our substitution rule and that would be all that we would need. But we're not that lucky. So let's try and break this down to figure out how could we approach this and still find an answer. So the first thing we could do is we could say this is equal to the square root of the limit as x goes to 2 of x cubed minus 2x squared plus x minus 2 all over x squared plus 3x minus 10 plus 3. The limit of a square root is equal to the square root of the limit. So this is our root law of limits. So there we go. We used one rule to make it a little bit easier to deal with. Well, unfortunately, we still have the 0 over 0 thing going on. But the problem is we can't do anything with that directly because we still have this plus 3 hanging around. So let's try and break that piece off so then we can just deal with our 0 over 0 limit. So this is going to be where we use the addition law of limits. So this is where we are able to get this to be equal to the square root of the limit as x goes to 2 of x cubed minus 2x squared plus x minus 2 all over x squared plus 3x minus 10 plus, whoa, where'd that come from? Okay, plus the limit as x goes to 2 of 3. Great. We moved out the plus 3 so that we can now have a single limit which is 0 over 0. So let's try and figure out how can we approach that one. So if it's 0 over 0, that means that hopefully we can get something to cancel. So we have these polynomials. Let's try and factor these polynomials. So we got, this is equal to square root of the limit as x goes to 2 of something that we'll try and factor, and we have plus the limit as x goes to 2 of 3. So let's try and factor those. So let's start with the denominator. So let's see, we got x squared plus 3x minus 10. So we know it's 0 when x is 2. So that means that there's an x minus 2 in there. So if there's an x minus 2, what's the other one? Let's see. Well, 2 times 5 is 10. So it's probably going to be an x with a 5, and we need them to add the 3, so it's an x plus 5. So that's what's on the bottom. But we also knew the top was 0 when we plugged in 2. So that means the top also will have an x minus 2 piece. And what's left? So if we factor out an x minus 2, it turns out what's left is an x squared plus 1. Okay? And now that we're inside the limits, we can cancel stuff. So that means this will cancel. Now, what law is that? That's just the law that says when we're able to cancel. Inside limits, we are able to cancel these sorts of things. This is where we have some cancellation laws. I don't remember exactly what our textbook calls them, but I've just always referred to them as like you can cancel inside a limit. So we got that, and now we don't have any division by 0, so that's going to be good. Let's break this down just a little bit further using some more of those laws that we can get. So the next thing is we can do is we now have division where the denominator is not 0. So this is equal to, we have the square root of the limit of the top of x squared plus 1 divided by the limit of the bottom, x goes to 2 of x plus 5, plus the limit as x goes to 2 of 3, and this is now where we're able to plug in. We can just plug in, so it's polynomials can plug in. So this is going to be equal to the square root of where we just plug everything in. So we have a 2 squared plus 1 divided by 2 plus 5 plus 3. This is the square root of 5 over 7 plus 3. So 3 is 21/7. 21 plus 5 is 26. Square root of 26 over 7. Not a super nice number, but that is what it's going to be. So if you need a little bit more time, go ahead and pause the video here so you can see everything that's going on, or go back and try it again. This is just a lot of practice. We need to be able to do these sorts of things to do anything in the future with calculus. So along with this, there's one other common thing that shows up on almost every test involving when we first learn about limits, and that's involving the squeeze theorem. So let's look at something that would need that. So let's say that, for example, we are asked to find what is, come on pen, here we go. What is the limit as x goes to 2 of x minus 2 squared sine of 5 over x minus 2? What's this going to be? Well, if we look at the graph of this, we'd have something like this. At 2, need a bit more space. We have something like this. There's 1, there's 2. The graph of this is looking something like that. So it looks, if we were to graph it at least, it would look like it's going to 0. It looks like it's going to this right there. But the challenge is, how can we show that? We need to find, the squeeze theorem says we need to find a function that is always bigger than that goes down to 0, and another function that's always smaller that also will go up to 0. And so that's the big challenge with these. We have to find a function that's bigger and a function that's smaller. So the way that I would do these is I would start by looking at, in this function, is there something that I know for a fact is always between two things? Well, sine. I know that sine is always between two values. So let's just start with that. I know that sine of x is always between 1 and -1. Okay. Now, if I change the x to be sine of 5 over x minus 2, does that change the range of sine? No, this isn't going to change the outputs that we would get. It's still going to be between 1 and -1. They're still very, it's behaving very differently, but it's still always between those two values. So now I've taken care of this entire piece. What I would like to do is I would like to just take this and multiply it by everything. So am I allowed to just have negative x minus 2 squared is less than or equal to x minus 2 squared times sine of 5 over x minus 2 is less than or equal to x minus 2 squared? Am I allowed to do that? The question when we're doing this is, am I multiplying by a positive or 0 number? Because if we multiply by a negative, the inequalities would have to switch, because if we have 2 is less than 3, multiplying both sides by a negative makes this no longer true. So in order for the inequalities to stay facing the same ways, we have to be multiplying by some positive value. So is x minus 2 squared never negative? Yeah, if we were to graph it, the graph of that would be this. It's always positive. It's always above the x-axis. So because it's always positive, that means that what we just did is perfectly valid. We multiplied by something that's always bigger than 0, or at least bigger than or equal to 0, which means that this is a valid thing that we can conclude. So what does that tell us? Well, this is how we're able to use the squeeze theorem. So the squeeze theorem says that if we have a function f of x that is always less than or equal to g of x, which is always less than or equal to h of x, then the limit as x goes to a of f of x is less than or equal to the limit as x goes to a of g of x is less than or equal to the limit as x goes to a of h of x. It says, the squeeze theorem says that limits behave nicely with inequalities. They do exactly what we think they should do when we're dealing with inequalities. And so, if we're trying to find the limit of this middle function, that might be a bit hard to do, but maybe these outside functions are much easier to do. So, using the squeeze theorem, that says that the limit as x goes to 2 of negative x minus 2 squared is less than or equal to the limit of x minus 2 squared sine of 5 over x minus 2 as x goes to 2, which is less than or equal to the limit as x goes to 2 of x minus 2 squared. Well, this first one and this last one, those are just equal to 0. So we got 0 is less than or equal to the limit as x goes to 2 of x minus 2 squared sine of 5 over x minus 2 is less than or equal to 0, which tells us that this limit as x goes to 2 of x minus 2 squared sine of 5 over x minus 2 must be equal to 0. That is the power of the squeeze theorem. Now, the only thing that got really confusing and can sometimes be a bit tricky is this part right here. When we are multiplying everything by some function, we have to be multiplying by something that's always positive. We can't multiply by something that's negative, because if we multiply by something that's negative, the inequalities are going to switch. And so that is the challenge that we have to deal with sometimes with these sorts of things. Especially if this had been an odd power, like say that was x minus 2 cubed. Well, the graph of something cubed is sometimes negative, which means that multiplying by x cubed would not have worked in this case, because sometimes it'd be negative. However, those situations, instead of multiplying by x cubed, multiply by the absolute value of x cubed, and then that's going to work. That is the nuance and stuff that can get a little bit confusing sometimes. Okay, let's do one last, or a couple more limits. So let's just go through a couple more limits and try and do these on your own. And then we will be able to move on to continuity. So, compute the following. Okay. Compute the limit as t goes to 0 of 21 over t squared plus 7t minus 3 over t. The limit as x goes to 5 of the square root of x plus 11 minus 4 all over x minus 5, and the limit as x goes to 0 of x to the 4th sine of 5 over x squared. Give each of these a shot, pause the video if you need, and try and compute what each of these limits would be. These are common ones that are similar to ones that would show up on quite a few different tests. So give each of them a shot and unpause the video when you are ready. Okay, I'm going to start with the last one, because the last one is very similar to the problem we just did. This is also going to be a squeeze theorem function. So what we'll do is we will be able to use very similar arguments to start with. Sine of x is between 1 and negative 1. So then that means that sine of 5 over x squared is also between 1 and negative 1, which means that negative x to the 4th is less than or equal to x to the 4th sine of 5 over x squared is less than or equal to x to the fourth, and then x to the fourth, that goes to 0, or negative x to the fourth goes to 0, x to the fourth goes to 0, so this is going to be equal to 0. Now, if this was a free response, you would need to have a little bit more work, similar to the amount of work that we had on the last problem. However, it wouldn't be too much more work than what we have currently written. You would just need to formally stick a limit in front of each and every one of these right there, and then that would be the work that you would need to do. So moving from the bottom up, let's now work on the second one. So the limit as x goes to 5 of the square root of x plus 11 minus 4 all over x minus 5. Well, if we try and plug in 5, we get the square root of 16, which is 4 minus 4 on the top, so that's a 0 on the top and a 0 on the bottom. Great. We can't plug in 5. What should we do now? Well, this is similar to one that we did a little bit earlier, where we have a square root that we would like to have gone. So to do that, we're going to multiply the top and bottom, not by the entire top, but the conjugate of the top. So we're going to multiply the top and bottom by the square root of x plus 11 plus 4. And so by doing that, the top is going to become the limit as x goes to 5 of x plus 11 minus 16, because that's 4 squared, all over x minus 5 times square root of x plus 11 plus 4. Well, continuing this becomes x minus 5 on the top, the limit as x goes to 5, of x minus 5 on the top over x minus 5 times the square root of x plus 11 plus 4. Now, these x minus 5s can cancel, so we're left with just a 1 on the top, and we just canceled out the dividing by 0 piece. So now we'll try and see, can I plug in 5? Now, this isn't one of those limit laws directly, but this is a combination of the quotient law, the square root law, and the addition laws, and then the substitution law. So we are able to end up substituting here, and this is going to be 1 over the square root of 5 plus 11 plus 4, which is a 1 over the square root of 16, which is a 4 plus 4. So this is 1/8. Great. We were able to figure that one out. So let's try and tackle this first one. Well, if we try and plug, we get 21 over 0 minus 3 over 0. So we got something over 0 minus something over 0. We might want to say that doesn't exist because we had something over 0, but that's not going to be the case. It only doesn't exist if you have just a single thing over 0. Here we have the subtraction involved, which means we first have to combine it before we can say that it doesn't exist. So the first thing we have to do is figure out how can I combine this fraction with this fraction. So we're going to need to get a common denominator. And so first, let's look at the factors of the different denominators. So t squared plus 7t, that's t times t plus 7, which means that this 3 over t, we just have to multiply that piece by t plus 7 over t plus 7 to be able to get that common denominator. So this is going to now be the limit as t goes to 0 of 21 over t times t plus 7 minus, let's see, 3t plus 7 becomes a 3t plus 21 all over t times t plus 7. Now if we combine these fractions, this becomes the limit as t goes to 0 of, we have 21 minus the quantity 3t plus 21 all over t times t plus 7. which is equal to the limit as t goes to 0 of 21 minus, let's distribute that negative through, minus and a minus, so that becomes 21 minus 21, so those two cancel. So we are left with a negative 3t on the top over t times t plus 7. T and t can cancel from the top and bottom. So those two can cancel. And so this is equal to, and we just canceled out the dividing by 0, so now we can plug in 0, and we get a negative 3 over 0 plus 7, so a negative 3 over 7. And that's how we would be able to go through and do each of these limits. All right, let's go and talk about some continuity. So let's go through and write down a few different functions. So we have f of x is equal to, it's a piecewise function, x squared minus 2 if x is greater than or equal to 1, and it's equal to x if x is less than 1. We also could have g of x is equal to, also a piecewise function, sine of pi x plus 2 if x is less than 0, 2x plus 3 if 0 is less than or equal to x is less than or equal to 3, and 7 if x is bigger than 3. And then maybe we have h of x is equal to x squared plus 7x plus 10 all over x plus 2. The question is, are these functions always continuous? So maybe for f of x, is f of x continuous at x equals 1? Or for g of x, is g of x continuous at x equals 0? How about at x equals 3? And then for h of x, are there x values where h is not continuous? Go ahead and pause the video and try and figure out if these are continuous at those different points. So let's start by reminding ourselves what it means for something to be continuous. So a function f of x is continuous at a at a point a if the limit as x approaches a of f of x is equal to f of a. Okay, so this is what it means for it to be continuous. So this actually means a few different things. First, it means that the limit exists, which is not always guaranteed, especially in piecewise functions. And then it also means that the limit is equal to f of a. And this also means that f is defined at a. So these are three different things that all could disqualify something from being continuous. So if we look at h, for example, in order for it to be continuous, f has to be defined there. So are there x values where h is not defined? Well, we're dividing by an x plus 2, so it might not be defined if we're dividing by 0. So that means that x can't be 2. So that means that h of x is not continuous at -2. Whoops, I forgot the negative sign. So h is not continuous at -2. The limit exists, the limit goes to a certain value, but h is not defined at -2, so it cannot be continuous at -2. Now, let's go to f of x, because f of x is defined everywhere, so we've taken care of the last condition. The question is, does the limit exist? So, at x equals 1, what's the limit as x gets close to 1 of f of x? So if we're looking at the limit as x gets close to 1 of f of x, the challenge is that it's not always one rule. If we're bigger than x, it's the first rule. If we're smaller than x, it's the second rule. So we have to break this up into two pieces. So the limit as x gets close to 1 from the positive side, so things that are bigger than 1. Here, things that are bigger than 1 are going to be using this first rule. So this is going to be equal to the limit as x gets close to 1 from the right of x squared minus 2. Oh, wonderful. This is a polynomial. We can plug it in. So this is going to be equal to 1 squared minus 2, which is -1. Perfect. There we go. So it's a -1 there. How about the limit as x approaches 1 from the left? Well, here we're approaching it from things that are smaller than 1, which means we're using the second rule. So this is the limit as x approaches 1 from the left of x, which is just 1. Uh-oh. -1 and 1, those are different. So this is not continuous at 1, because the limit does not exist. Now let's go ahead and look at g of x. G of x is a little bit different because there's two different things that we're checking. We need to check both of those different values. So let's go through, clear up a little bit of space, and work on that one. So for g of x, let's start at 0. So we are going to have to do two different limits. So the limit as x approaches 0 from the left of g of x, and the limit as x approaches 0 from the right of g of x. So as it approaches 0 from the left, we're approaching from things that are smaller. So that's going to be the limit as x goes to 0 from the left of sine of pi x plus 2. Now, sine is one of those functions we're allowed to just plug into when we have a limit. So this is going to be equal to sine of 0 pi plus 2. Sine of 0 is 0. So this is equal to just 2. Okay? So we were able to calculate that one. Now, if we approach it from things that are smaller, or things that are bigger than 0, so this is going to be the limit as x approaches 0 from the right, things that are bigger. Our bigger function is just the 2x plus 3. Well, that's going to give us 2 times 0 is 0 plus 3 is 3. Okay, limit doesn't exist. Bummer. That means it's not continuous there. Now, if we had changed this, just a little bit, so instead of a plus 2, it was a plus 3. Well, and that's going to change this a little bit more. So that becomes a 3 plus 3 equals 3. If this was what we were given, then g of x would be continuous at 0. Oh, wait, we have one more thing we have to check. All that guaranteed was the limit exists. We have to show the limit is equal to f of a. So if we plug it in, or not f of a, g of a, so g of 0, okay, oh, that's this condition. So that's going to be 2 times 0 plus 3 equals 3. Perfect. All three conditions were satisfied. So that means that g of x is continuous at x equals 0 if we changed that number to be a 3. As it was earlier with the plus 2, that would not have been continuous there. Now if you were to check at 3, the limit is going to be doing different things again. So we would have the limit as x gets close to 3 from the left-hand side of g of x. That would be the limit as x goes to 3 from the left of 2x plus 3, which is going to be 2 times 3 plus 3, which is 9. But then from the right, the limit as x goes to 3 from the right of g of x. That is the limit as x goes to 3 from the right of 7, which is 7. Those are not equal, so it is not continuous at x equals 3. So those are some of the different things that we could do. Let's do one more continuity example. Actually, let's do a few more so that we can have more than just one example. This might be something that you could be asked on a test. You might be asked, solve for c so that f of x is continuous at, let's say, x equals 1, where we might have something like f of x is equal to c times sine of pi x plus 3, and then cx minus 1, where we have this variable c showing up in both of them, where this is true if x is less than or equal to 1, and this is if x is bigger than 1. So go ahead and try and solve this to figure out what value of c do I need to make so that f of x is continuous at 1. Okay, so let's go through the different things that we need. First, we need the limit to exist, which means we need both of these to go to the same thing. So if we look at the limit as x approaches 1 from the left of f of x, this is going to be the limit as x approaches 1 from the left of c times sine of pi x plus 3. And this is one of those functions we can just plug in. This is equal to c times sine of pi plus 3. Sine of pi is 0. So this is equal to 3. Okay. That made that pretty easy. On the other hand, the limit as x goes to 1 from the right of f of x, well, that's just going to be the limit as x goes to 1 from the right of cx minus 1, which is equal to c minus 1. We want both of these to be equal. So that means we need c to be 4. Now the question is, does that also make the other conditions also hold? So the other one was, okay, we just made it so the limit exists. It goes to the same thing from both sides. We also have, it's defined there, because we have the possibility of x being 1. Now the last thing we have to do is we have to then also include that f of 1 is equal to 4. Well, if we plug in x equals 1, oh no, not equals 4, equals the value of the function there. C is 4, but the value of it's 3. So if we plug in x equals 1, okay, it does turn out to be 3. So c equaling 4 is actually our solution for this particular problem. Okay, let's do one more so we can figure this out. So we have is f of x equaling 7 times x minus 3 cubed over x minus 3 continuous for every x. In other words, no matter what x I use, is this going to be continuous there? Well, it turns out that no, because this bottom, that is not going to be allowing every x value to be inputted into this function. We know that x cannot be 3 because we can't divide by 0. Even though the top is 0 and we can find the limit as x goes to 3, this is not continuous at 3 because there is going to be a problem when we divide by 3. If we were to look at the graph of this, it would look something like this, where there's this tiny little hole right here. That's what this is dealing with. We can't have this be continuous there because it's not defined there. Now let's go to the very last problem of this review that I'm going to go through. And this is going to be a common one on tests. I don't know if it'll show up on this particular test, but it is something that you would probably expect to show up on a test for Calculus 1 when you're talking about continuity. We might be asked something like, show that f of x equaling x cubed plus 4 and g of x equaling 2 sine of x intersect at least once. How on earth does this connect to continuity? Like, sure, x cubed plus 4, that's continuous. Sine of 2x, that's continuous. But how on earth can I use that to show that they intersect? It turns out that the way that this connects is by using what's called the Intermediate Value Theorem. Or often abbreviated the IVT. So go ahead and try and figure out how we could use the Intermediate Value Theorem to do this. If you don't know it, don't pause the video yet because I'm about to explain it. If you do know it, feel free to jump forward about 30 seconds. Now, the Intermediate Value Theorem, what that says is it says that if f of x is continuous, for all x in some interval a to b, the Intermediate Value Theorem says that if f of x is continuous for all x in that interval, then if we have some number so that f of a is less than or equal to n is less than or equal to f of b, or the other way around, so f of a is the bigger one, then there is some value c in that interval where f of c is equal to n. So that is what the Intermediate Value Theorem says. So try and think about how we might be able to use that to show that two different continuous functions intersect. The way we could do this is we can think about what does it mean for them to intersect. So if they intersect, then we know that f of x is equal to then we know that f of x is equal to g of x, and f of x minus g of x would be equal to 0. This gives us a hint at something we could do. If f of x minus g of x equals 0, let's let 0 be our n value. So that means we need to come up with some new function. So we are going to say, let h of x be f of x minus g of x. This is the first step anytime you need to use the Intermediate Value Theorem and show that two different functions intersect. So if h of x is f of x minus g of x, then we have h of x is equal to x cubed plus 4 minus 2 sine x. This is continuous. We can do this because if you add continuous functions together, that's continuous, and x cubed, 4, and sine of x, all of those are continuous. So we have a continuous function. We got this first condition done. F of x, or in this case, h of x is continuous. And it's continuous everywhere. So now what we have to do is we have to find an interval where on one side h of that number is smaller than 0, and another one where h of that number is bigger than 0. So let's say that, for example, we look at h of, I don't know, let's try just h of 0, see what that number is. That's going to be 0 plus 4 minus 2 times 0, that is 4. Okay, h of 0 is 4. Great. We have something that's bigger than 0. That means we now need to find something that's smaller than 0. Okay? What might we try with that? Let's see. Well, let's see. X cubed, if we were looking at the graph of that, x cubed is doing something like this. Then adding 4 is going to be moving it up to something like this. And then the 2 sine x, that's going to make it kind of like wobble around that. So that means if we pick something far enough negative, it should still be negative. So that's what we're going to try and do, is find a negative number that's going to work. So let's try h of negative, I don't know, let's try h of negative 2. Let's see what that is. So this is going to be negative 2 cubed is negative 8 plus 4 minus 2 sine of negative 2. Okay, I'm not really sure what sine of negative 2 is, but what we have left is negative 8 plus 4, that's a negative 4 minus sine of negative 2. Okay, well, 2 sine of negative 2. Well, let's see, sine can never be anything bigger or smaller than 1 or negative 1. So that means that I could make this as big as possible by making it a negative 1. So this is, let's see, less than or equal to negative 4 plus 2, which is negative 2. So h of negative 2 is definitely negative. If you're not really seeing it there, replace negative 2 with something that's even more negative, like h of negative 100. That is definitely going to be negative. So that means that we know that h of negative 2 is less than 0, or less than or equal to 0, which is less than or equal to h of 0. So then, by the intermediate value theorem, somewhere in the interval 0 to negative, not 0 to negative 2, negative 2 to 0, somewhere in the interval negative 2 to 0, there is some c where h of c equals 0, so f of c minus g of c equals 0, and f of c equals g of c. That is how we would be able to use the intermediate value theorem to help us solve this problem. I hope this was helpful. Good luck on your tests, and I will see you all later. And feel free to check out some of my other videos, because I do have quite a few that talk on a lot of these topics. So have a great rest of your day, and good luck with all of your math.